Welcome to Network Theory Lab, and today in this video we are going to learn how to analyze the series RLC circuit. So let's begin this discussion. So here you can see this is our RLC circuit, okay, in which we are having these three components: resistance, inductance, and capacitances, which are connected in this series. So we have to analyze this circuit and we have to find it out what will be the resonance frequency of this particular circuit. So here we have to connect one AC voltage source. So though it is shown here to be a DC source, but we have to connect one AC voltage source, and then we have to find it out what should be the resonance frequency of this particular circuit. Okay, so first of all, if we see, because it will be it is containing the inductances and capacitances, then the total impedance offered by this circuit is given by this particular expression: Z equals to resistance R plus J omega L minus J upon omega C. Okay, so this is also written as XL, okay, which is the inductive impedance, and this will be your XC, which is your capacitive impedance, right? So this way, the total impedance of the circuit will be given by this particular circuit, this particular equation, right? So normally, to find the resonance frequency of the circuit at the resonance frequency omega naught, normally what happens, this inductive impedance and capacitive impedance will be equal, right? And that time this two will be cancelled out, and this resistance or impedance offered by the this particular circuit is equals to pure resistance. Okay, so by following that particular equation, that J omega L will be equals to J omega C, we can have this particular expression of omega naught. So at omega equals to omega naught, there will be a certain resonance that will occur into the circuit, right? So omega naught is equals to, you can find it out, it is 1 upon root over LC. So from here, if you calculate the frequency F naught, then it will be coming out as, from the calculation, 5033 hertz, right? So here I have made this simple observation table. Okay, so we have to change the frequency. Okay, so first of all, we have to apply a sinusoidal wave over here. Okay, and then we have to keep its magnitude constant, and we have to keep on changing the frequency of the applied signal, right? So these are the typical values of the frequency that we have to apply. Okay, so you can see this total 14 number of such different frequencies I have applied. And then we have to measure the voltage. Okay, we have to measure the voltage across the this inductance, and we have to also measure the voltage across this capacitance, right? Then we can also measure what is the current passing through this particular circuit, right? So here you remember that whatever the voltage we are going to measure across the inductance and the capacitance, right, there will be a phase difference of 180 degree. So that's why I have putting here a negative sign. Okay, so here you can see the experimental setup, okay, that I have implemented onto the MultiSim. So this is our RLC network. Okay, so here I have taken this resistance value equals to 100 ohm. Okay, and this inductance I have taken of 1 millihenry, and this capacitance I have taken equals to 1 microfarad. Okay, so here I can you can see I have connected, this is our multimeter. Okay, and you see this multimeter is measuring the AC current, right? Because this AC is selected right now. And here I have connected 2 voltmeters. So right now these 2 voltmeters is measuring the voltage, and this should be a AC voltage, right? So when we are measuring the AC voltage or current, you remember it will be measuring the RMS value. Okay, it is not measuring the peak values, it is measuring the RMS values, right? So this is voltage, this is again your AC quantity, right? So this way we have to make this circuit. Okay, we have to connect this to voltage source, voltage voltmeters across these two components, right? Here I have also connected the oscilloscope to visualize this signal. Okay, you can visualize what kind of waveform is coming across this two component, right? So if we start this experiment, see here I have connected one function generator. Okay, And from this function generator, we have to give the various frequencies of our input sinusoidal wave. Okay, so the sinusoidal wave I have selected here, and the peak value of this sinusoidal wave we have taken equals to 10. Okay, so this I will be kept constant. Okay, we don't need to change this value, but we have to change the frequency value, because for the various values of the frequencies, we have to obtain the voltages across these two elements. Okay, and also we have to measure the current, and later on we can also draw the frequency response of this particular series RLC circuit, right? So here you can see this value. So first we have to start this experiment from 1 kilohertz. So if you substitute here equals to 1 kilohertz, right? So if we make it 1 kilohertz, and if we execute this circuit, okay, here you can measure the various parameters that I have already noted down there. So here you can see this is 38.8 milliampere current. Okay, so that I have noted down here. It is approximately 0.039. Okay, so it is 39 milliamperes, right? So this is the value. Similarly, you can measure what is the VL and VC. So if you see this VL and VC, right? This VL and VC, okay. So this is coming out as 0.244. So that I have noted down here, okay, 0.244. And similarly, you can measure VC, okay. So if you see this VC value, then you will find here, this is our VC, so it is 6.156. So we have to just put one negative sign, because there is a 180 degree phase shift between the two voltages. Okay, so that 180 degree phase shift you can also observe from this oscilloscope. Okay, here you can see this, right? So here you can observe these values, right? So let me change this voltage sensitivity a little bit, so that this waveform will be properly visible, right? Okay, so let me change it. Fine. So now here you can see certain waveform is visible right now. Okay, so we have to properly select the time scale, so that this waveform will be properly visible, right? So let me change the time scale a little bit. Okay, so here you must be able to see there is a red signal, okay, and there is one white color signal, right? So here you can see this white signal, which is the white waveform which is coming here, is actually, it is a voltage waveform which is across your capacitor. Okay, this capacitor, the channel B, this voltage is actually connected, right? So we have connected the voltage waveform across the capacitor to channel B, and it is coming in white color, right? And in channel A, the voltage across the inductor has been connected, right? So this is in the red color, so it is coming out as red color. Okay, so here you can observe that at present this circuit, the voltage is across this particular the voltage across this inductor is less than the capacitor, right? So capacitive inductance must be greater in this case, okay, for this particular frequency, right? And the inductive capacitance, inductive impedance will be less, right? And capacitive impedance will be more at this point, right? So now, if you change the frequencies, right? So this way you have to first make the measurement, okay? And here you can see, I will be not showing all of these values. I have already conducted this experiment, so you can just try to verify all these results, okay? So I will be showing you few of the readings. So you just see this 7th reading, okay? If we make this frequency 5025, okay? If we make this 5025, okay, you can observe this change. Okay, so what will be the change in the waveform that we have to observe? So if I make it, let us say it is 5025, okay, or 502, okay, that time you can see, if we keep it 5020, okay, this is 5020 hertz, right? So let me make it, sorry, it is already kilohertz selected. So let me make it 5.02, right? So now it is 5.02 kilohertz, right? 5.02. So it is 5.02 kilohertz. So now if we execute it, here you can see there is a difference, okay? And now you can see this waveform, right? We have to properly adjust this time scale. And now you can see this two voltage waveforms are having the similar magnitude, okay? The red one and the white one. So this, as I said, that this white one is connected across the capacitor and red one is connected across the your inductor. So here we can clearly we can observe this signal, right? So here we can see this two voltage sources are actually having the same voltage value. Okay, we have kept the sensitivity of channel A and B similar. Okay, and here you can see the voltages coming across these two components are similar. The same values, the same magnitudes we are getting. And one thing that you can note down is that when this red waveform is having a peak value, at the same time this white waveform is having its minimum value. Okay, and therefore it is having its 180-degree phase shift that we have noted down there. Okay, so this way you can observe the waveform in the oscilloscope also. And here you can observe, because both this waveforms are having the similar magnitude, we can say that at this particular frequency, this capacitive impedance and inductive impedance offered by the circuit are same. Okay, the magnitudes will be same, and at this point this 2 is going to be cancelled each other because of its negative sign, and therefore the overall impedance offered by the circuit is going to be resistive. Okay, that you remember. Fine. So this way you can observe. Okay, and you can again observe these values, right? You can observe these values in voltage across the inductor and voltage across the capacitor, that I have already noted down there. Okay, 2.238 and minus 2.235. So it must be almost equals to a similar value. Okay, remember that. So let me just make it 5020. Okay, so okay. So now this must be a similar value. So it is almost similar. It is coming out as almost similar, and because it is a negative sign, must be these two voltages will be cancelling each other, right? And this impedance will cancel each other, right? And therefore this impedance offered by the circuit will become resistive. Okay, at this point of time, when your frequency is 5020 hertz, that time this current I you can see from the circuit, this current I is coming out as a 70.711 milliampere, that I have noted down here. Okay, so this is our current value. So in this way you can conduct this experiment. You can observe that if we increase the frequency above this 5020 hertz, right, at that time you can observe one thing. Before that, if you see, it was a capacitive impedance offered by the this particular circuit. Okay, but when we increase the frequency further beyond this 5020 hertz, then the impedance offered by becoming more inductive in nature. So that we can also observe from this graph itself, this particular waveform itself. Okay, so let me try this particular frequency. Okay, 8,000 or 9,000, let us say. So if we go to this 9,000, okay, then you can observe this value here. So if we make it 9,000, let me make it 9 kilohertz. So if we make it 9 kilohertz, and then if we execute this circuit, okay, you can observe this waveform. Now you can see this white waveform is having less magnitude as compared to the red one. Okay, and we know that this red is coming across the inductor, and therefore this circuit is becoming more inductive in nature rather than the capacitor. So this way you can conduct your experiment. You can just try to observe all these values, whatever I have shown in this table. Okay, so here you can see this. I have noted down this 4 parameters. One is frequency, then the voltage across the inductor, voltage across the capacitor. Okay, remember that these values will be your RMS values. Whenever you are connecting your multimeter, it will be giving you a RMS value, right? And then we have to also measure the series current I. Okay, it is again going to be a RMS value. Fine. So now here you can see we can plot the frequency response of this particular circuit, right? So to plot this frequency response, okay, normally we have to select this current I, and then we have to select this frequency. So it will be a frequency versus current plot. Okay, so here we can also have this option. Okay, in Excel. So here you can go to this particular chart, and then you can go to this scatter plot. So here we can go on plotting this one, right? And then later we can also change this axis. Okay, we can modify this axis to log scale. So you can go to the format axis, and then you can just make it logarithmic scale. So this way you can plot this frequency response of this filter. Okay, so here you can see that at a certain point this current is getting maximum. Okay, we are getting a maximum current at certain points, right? And then the current at both the sides, it is going to be reduced, right? So here we can also calculate what is the half power point. Okay, half power point frequencies, right? So normally this half power point frequencies, if you see in the books, it is defined in this way, right? So you can see we can have the two half power frequencies, omega 1 and omega 2. Okay, so normally these are the frequencies at which the current response is becoming 70.7% of the maximum response, right? So it will become 0.707 times of the maximum response. So here you can see the maximum response that we got is around this particular frequency 5020, which is 0.071. So I have noted down these two frequency values, 1460 and 17,300 frequency. Okay, 17.3 kilohertz and 1.46 kilohertz. So at this point, you can see this current. Okay, this current is becoming 0.707 times of this maximum current 0.071. Okay, so this is the maximum current 0.071 milliampere. So this is your 70% of this maximum current. Okay, so that you can observe. So this is your frequency response, right? So this way we can calculate the means what will be the resonance frequency of the circuit, either by following this particular formula. Okay, omega naught equals to 1 upon root over LC. Okay, or you can also find it out by having the experimental observations. So normally what we do is, if you don't want to calculate it by the formula, just you have to keep changing this frequency values, right? So once you will be keep changing the values of frequencies, we have to note down that particular frequency at which this VL and VC, the magnitude of this voltage drop across the inductor and capacitor will become equal. Okay, so here you can observe here these two values are almost equal. Okay, and therefore this frequency will become your resonance frequency. So that way we can also find it out. Fine. And every at other points you can note down that this either VL is greater than VC or VC is greater than VL. So that you can note down. We are talking about the magnitude, you remember. Okay, so I hope you must able to conduct this experiment. So you try this experiment onto the breadboard. Okay, so there you can connect the multimeter, okay, to measure the voltages. And if you have the facility to having the oscilloscope, you can also connect the oscilloscope. You remember that this connection of the oscilloscope is not necessary, it is not mandatory to connect. With this multimeters, you can also conduct your experiment. So just you take these two multimeters to measure the voltages across this component, and one multimeter you have to connect to measure the current. Okay, and if you have the oscilloscope, then you please connect, and you will be having more insight because you will be able to observe the waveform. Okay, and then you will be clearly able to visible that there is a 180-degree phase shift between the two signals, two waveforms. And obviously the magnitudes are different. Okay, sometimes this white waveform is having more magnitude, and some other times this red waveform will have less magnitude. This way you can observe that differences, right? And then at the resonance frequency, both the magnitudes of this waveforms will become equal. So I hope you must have able to understand something from this lecture. So try to implement this onto the MultiSim as well as onto the breadboard. So if you have any doubt, then you can ask me by dropping your comment into the comment section. So thank you for watching this video, and stay connected with the channel for more updates. Thank you.